I'd like to talk about predator-prey system this time. So first, let me introduce the general form of predator-prey interaction functions. So the interactions exist in many dynamics in nature, but among many types of interactions, predator-prey is easy to catch. So there are lots of models to express the predator-prey relationship. So the general type of predator-prey system can be described by this ODE system. Here, if you put the derivative of f with respect to v is negative, and the derivative of g with respect to u is positive, then we say this is generally means the predator-prey relationship, because the increase of v make the predator to decrease, and the increase of u make the predator increase. So this is the general condition for predator-prey relationship. So the earliest type of predator-prey relationship is the classical Latka-Volterra relationship, which is described by this response function. Here, the response function f is a1 minus e1v, and the function g is minus a2 plus b2u. So the response functions are linear in terms of u and v. And this system is proposed in 1925 or 1926. These two persons proposed the system, the very same system, independently. And let's have a little bit complicated predator-prey system. No. This page talk about the solution of the classical Latka-Volterra system. The classical Latka-Volterra system can be directly solved. So the solution UTVT should satisfy this conservation law. So we see that the solution make a contour in the phase space, u-axis and v-axis. So the solution makes a contour. And this depicts the phenomena that occurs in nature that shows the predator-prey cycles. Okay. And if you put the in-species competition term, this term minus b1u and minus c2v, and these two terms describe the phenomena that if the population inside the predator increase, then the individuals in the predator, they should compete each other. So the increase of u make decrease of ut when the population of u is highly enough, and the same for the predator species v. And in this case, we don't have any conservation law. Instead, the solution describes this type of graph in the phase plane. So the solution converges in time to a constant steady state. And this is another predator-prey type of system. Here we had assumed the recurring hunters. So that means when the predator population density passes some constant number, and then we put the interspecific competition. So that makes to decrease the predator population. So in this case, the solution shows similar converging behavior to a constant steady state, but the speed in time is faster than the previous case. Okay, so there are lots of models for predator-prey systems. So if I introduce two more, then this one is Kerr-McKendrick predator-prey model in epidemiology, and this one is in microbial ecology. And the system from ecology, microbial ecology, is also used in biochemistry or fisheries. Here, the main topic of this talk is about Holling type predator-prey interaction. In nature, the predation rate, the predator response, may not be linear. So the classical Latka-Volterra model assumes that if there are more prey, then the predator population will increase. But that case may not be always true. So here, Rosen-Zweig in 1971, he used 6 different type of mathematical models for predator-prey type or parasite-host interaction, and he found that sufficient enrichment, if there are sufficiently many prey population, that may cause the extinction of the predator. So the higher concentration of prey, higher density of prey may not be helpful for the predator. It may make the predator extinct. So the predator response in that case should not be linear for U and V. And here, Holling type functional response depicts that case where if there are sufficiently large number of prey, that increase the ability of prey to defend or disguise themselves from the predator. So that phenomena can be called group defense. So in nature, we can see some examples of group defense, like this ox. When they form a small group, the attack by the wolf, their attack with rare success. But the musk ox is only one, then the wolf attack is always successful. So this case is an example of group defense. And another example of group defense can be found this large swarm of insects. So when the insects form a large swarm, then the predator attack is not successful. So how do we describe this kind of situation of group defense? So we have put this term of response, the response function or predation rate. So if you put this predation rate, when you increase the U population, the population of prey, that causes the predation rate decrease. So that depicts the case of group defense. Okay. So in this paper, we had put the diffusion rate D1 with D1 and D2, the diffusion coefficient, with the Holling type response functions with this group defense type of predation rates. So here, the coefficients are all positive constant, and here for the constant A2, this A2 can be positive or 0 or negative. It can have any sign. So here I'd like to present some results about the asymptotic behavior of the solutions of the diffusive Holling type predator-prey system. And I'd like to present 4 theorems. In Theorem 1, the conditions for the system to have constant positive steady state U bar and V bar will be shown. So, and Theorem 2 in Theorem 2, we will investigate the Holling type bifurcation phenomena around this positive steady state for the parameter Q. And this parameter Q was the constant in the group defense type of predation rates in the model. In the model here, Q is here in the group defense type of predation rate. So in Theorem 2, we will investigate the bifurcation phenomena about the parameter Q near the positive constant state. And in Theorem 1 and 2, we will study the ODE type of system. And in Theorem 3 and 4, we will study the diffusive system. And we will see the effects of diffusion rates for the asymptotic behavior. So in Theorem 3, we see that diffusions may cause the instability of positive steady states under the assumption that assured the stability for non-diffusive system. And in Theorem 4, we will see another effects of diffusion that changes the bifurcation value Q compared to the non-diffusive system. Okay. The condition for the diffusive system to have a unique positive constant steady states can be obtained by direct computations. So we'll set the response function ut equals u times this function, the diffusive response terms 0, and for vt we have this response function. So if you set two functions 0 and 0, then you will find the conditions to have a constant positive steady state. Usually this one, u bar and v bar, by some hard-working computations. And if you need to assume this condition in order to have this u bar and v bar both positive constants. So here, this quantity should be positive. And here, we are assuming this constant A2 negative. So this term will be negative large number. So inside of this parenthesis will be negative. So with this negative sign, this quantity will be positive. So the parameter Q need to be assumed to be less than this quantity in order to provide the positive constant steady state u bar and v bar for the Holling type predator-prey systems. And I'd like to talk about the Hopf type bifurcation phenomena for the Holling type system. And in order to have Hopf type bifurcation, we need to check two conditions, H1 and H2, satisfied. So for the condition H1 provides the eigenvalue of the linearized matrix is purely imaginary at this bifurcation value. And around the bifurcation value, the real part of eigenvalue should be non-zero. So the condition H2 is the transversality condition. So if we have these two conditions satisfied, then we see Hopf type bifurcation occurs. Then we have a small amplitude limit cycle solutions around this positive steady state. Okay, so we will see what conditions are required for the parameters A, B, and C, and Q to satisfy these two conditions for the Hopf type bifurcation. Okay, so the results is described in Theorem 2. when this condition A2 is negative and this value Q is less than this quantity, is to provide for the system 1 to have the positive steady state, positive constant steady state. And besides these two conditions, if we assume this condition, then the Hopf bifurcation occurs near this positive steady states, and the parameter value Q is obtained as this quantity. So if you only assume this condition, the conditions H1 and both H1 and H2 will be satisfied. Okay. The proof consists of the computations using the matrix A and look at the eigenvalues. So in the computations we see that determinant of this linearized matrix, the community matrix, is always positive. So if you compute the determinant, we obtain this quantity, and U bar and V bar positive, and all these constants and Q and U bar all positive. So we see the determinant is positive. So we only need to check about the trace part of A. And here, this part is negative and this part is positive. So we have to decide the conditions that decides the sign of trace of A. So if we have trace of A is negative, then this constant solution is linearly asymptotically stable. And if trace of A is positive, then this solution will be unstable. So solving the equation trace A equals 0, we'll find the bifurcation value, the bifurcation parameter, this value for the system, for the Holling type system. Okay, so well, the computations for trace of A, we will need to use the equations from the system, and you obtain this expression for trace A, and the coefficient, the outside of the parentheses is just constant coefficient. And if you reduce this part more, then you obtain this one. So here we can see the quadratic equations of Q. So from that quadratic equations of Q, you can determine the parameter value for the bifurcation. And yes. So after we found this parameter value for the bifurcation, we have to check the transversality condition, which was this. So we'll see under the assumption that we had put in the theorem, we'll see if this transversality condition is satisfied. If you look at the expression for the eigenvalue lambda, then under the square root we have negative value. So the real part of lambda is the half of trace of A. Okay. So the real part of lambda is half of trace A, and if you take derivative of this real part of lambda with respect to Q, it should be non-negative. It should be non-zero to satisfy the transversality condition. And these computations shows the equivalent form of this condition. Okay. So we had used this expression for trace of A because we obtained that trace of A is equal to this quantity, and the coefficient A1 and B2 doesn't matter with parameter Q. So we just need to take derivative of this part, and that derivative reduces to this expression. So we have to check this one satisfied in order to check the transversality condition. Okay. Then so here we had to put the value of Q here. We have the parameter value, the bifurcation value of Q here. So the value of Q plus minus star was obtained as this value by solving this quadratic equation of Q. So if you use this expression in that equation, it reduces to this condition. So we will check this condition is satisfied. So the assumption that we had in the theorem, in the statement theorem, was this one. And if we have this condition, under the square root is positive, and here this part, the two terms in the beginning are also positive. So between this plus and minus, when we have this minus sign, the plus positive part and the square root is positive, and A2, we assume that A2 is negative, so altogether this is positive. So this negative case is always true with this assumption. And we just need to check the plus part. It's not zero using this condition. And that's easily checked if you take square of the two terms and the square of the third term and subtract it from the first term squared. And then we have this, if you do some computations, and then we obtain this one. And here we see that the square part, okay, so these two terms inside this angled parenthesis, that's assumed to be positive. And here A2 is negative. So we have only one sign of this quantity. So that means if you do the factorization, then this plus case is also not zero. So we have checked that the H2 condition, the transversality condition for Hooke type bifurcation is satisfied if we have assumed this condition in the theorem. Okay, that condition we have assumed can be stated in this form if you do the factorization. Okay. So in this case, the ratio of B1 and A1 should be less than A2, the ratio of B2 to A2 times some positive number. So this rate should be less than compared to the A2 and B2 rates to provide the Hooke type bifurcation. And now let's talk about the diffusive case. The effects of diffusions to the stability. So here we obtain the conditions for the non-diffusive system to have positive constant steady states and the conditions for the Hooke type bifurcation. And here, if the diffusion rates D1 and D2 satisfy this inequality, and then the positive steady states becomes unstable under the assumption that provided the non-diffusive system have this steady state stable. So the diffusion rate changes the stability of these points for the diffusive case compared to the non-diffusive case. So you see where comes this condition about the diffusion rates. And okay, let's see. So here we will use this form this form for the solutions for the diffusive system. Around the constant steady state U bar and V bar, we will consider the form of the solution having exponential part and cosine, and exponential part and cosine for both U and V. And we'll look at the value, the sign of lambda for the exponential functions. So if we obtain the lambda value, positive lambda value, that will cause the solution diverge out from U bar and V bar, that make the solution unstable. So we'll see the sign of lambda and lambda there. So if you plug in this solution to the equation, to the characteristic equation, you obtain this equation. Here we have the quadratic equations of lambda squared and the constant terms for lambda. And here we'll find the condition that this equation has a positive solution for lambda. Then that can be checked by looking at this part. If this part becomes negative, then one of the solution, lambda, will have positive sign, right? So we'll put a function k beta squared for this term, because this term can be seen as a quadratic equations of beta squared. Beta is inside of the cosine function. So for this term, we have the function k beta squared, and here beta squared term is there, and another beta squared is there. So if this function is negative at some value, then we will obtain a positive solution of lambda, and that will make the solution unstable. Right? So in order to check if this part becomes non-negative at some value beta squared, we will just need to check the minimum value of this k. So the minimum value of this function is written as this function. So since the function k is quadratic function, so you can easily find out the minimum value of the quadratic function. That is this function. So, well, the minimum value may not exist if we don't have this condition, because the variable in this equation is beta squared. So if the minimum occurs at some negative value for beta squared, that doesn't make sense. So the minimum value of this function should occur at some positive value for beta squared. That is provided by this condition. So this condition provides the minimum value, k minimum exists. And here, the minimum value of k becomes negative if we, here d1 and d2 appears in this part. So if d2 over d1 satisfies this condition, we see that this k minimum becomes negative. So under this condition, the k function here, the k function has negative value, and it causes some positive solution of lambda, and the solution becomes unstable. Okay, so we have seen the effects of diffusion in this form that causes the solution U bar and V bar to make it unstable under the same condition that made the same solution stable for the non-diffusive case. Okay, and the last theorem shows the effects of diffusion terms that cause the bifurcation parameter, the bifurcation value, make the bifurcation value bigger than the non-diffusive case. So the Q star D is the bifurcation value for the diffusion system, and this Q plus minus star was the bifurcation value, Hopf type bifurcation value for non-diffusive case. So we'll see when the diffusion rate satisfies this condition, D1 is large enough than D2, then the bifurcation values are different for diffusion case and non-diffusion case. So here, to obtain this bifurcation value, we'll use the same type of solution, this type of solution for the diffusive case. And then, in order to find the bifurcation value, we will solve the equation K minimum is 0. That's this equation. And if you solve that equation, first simplify that equation, then we obtain this equation using the solution U bar was obtained as this ratio. And then the equation K minimum equals 0 reduces to this equation. And here we see the terms, the ratio D2 over D1 comes here. And when this ratio is very small, it's almost 0. And then the solution, the equation, in this equation, this part will become almost 0. So we will see only the first part of this equation. And here, the solution, we are solving for the parameter Q. The solution of this part, the Q solution of this part, yes, we will solving that part for Q. And the solution, well, since this is factorized, the solution of this equation for Q is this one or that one. And we can compare the size of these two solutions of this equation. And so these two values are the bifurcation values for the Hopf type bifurcation. And if you compare this parameter value for diffusion case compared to the parameter value for non-diffusive case, you can compare the size. Okay? The assumption that this part is positive, we will see this parameter value for non-diffusive case is less than this value. So when this D1 is large enough than D2, so this ratio is very small, almost 0. And then the parameter value of diffusion case is larger than the parameter value for non-diffusive case. Okay. So there was the second effect of the diffusion rates for the Holling type predator-prey system. Okay, let me close my talk here.
Do you have any questions or comments?